Hello, and a very warm welcome to Kognito Key. I am absolutely thrilled to have you here today. So, we're going to be unpacking a really fascinating, somewhat hidden phenomenon that's essentially stealing energy from inside our everyday electrical machines and just dumping it as wasted heat. You've probably guessed it, it's called hysteresis loss. Let's dive right into this explainer and see exactly what's going on beneath the surface. Real quick, our agenda for today covers the hidden energy thief. Then we'll check out molecular magnets and friction, the hysteresis loop itself, how we actually calculate that magnitude, and finally, the engineering solution. All right, Section 1, the hidden energy thief. Whenever you're running electrical machines, like transformers, motors, that sort of thing, you know they get hot. And that heat isn't just an annoyance, it's actually a massive waste of energy. But where is it coming from? Well, hysteresis loss is essentially the work done by the magnetizing force against the internal friction of the material's molecules, which then just gets wasted as heat. So this heat isn't magic. It's a direct, physical result of work being done against molecular resistance right there inside the material. Okay, let's move on to Section 2, molecular magnets and friction. Let's visualize what's actually happening at the microscopic level. When you apply a magnetizing force, the molecules inside the magnetic material act like tiny little magnets, and they all align themselves in one direction. But because we're dealing with alternating current, that magnetic force is constantly reversing. And every time it reverses, all those molecular magnets have to physically flip. The catch? They resist that change. They don't want to flip. And that resistance creates internal friction. It's literally just like vigorously rubbing your hands together. That physical friction generates heat, right? Same exact concept here. Overcoming this residual magnetism basically eats up a chunk of the magnetizing force and spits it out as wasted heat. Which brings us nicely to Section 3, the hysteresis loop. So how do we represent this mathematically? When you plot a single complete cycle of magnetization on a graph, it traces out a shape that we call the hysteresis loop. If you integrate that curve, specifically the integral of h dB, you get the area inside the loop. And that area is super important because it directly equals the total work done or the energy wasted per unit volume during just one single cycle. The takeaway here is incredibly simple. A bigger area means more wasted energy, period. And to figure out the total power being lost over time, it's quite straightforward. We just take the area of that one loop, measured in joules, and multiply it by F, which is the frequency or the number of those magnetization cycles happening every single second. That gives us the total hysteresis loss in watts. It's a really elegant way to bridge the gap between one microscopic molecular flip and the continuous power drain you see in a running machine. Let's jump into Section 4, calculating the magnitude. So how do engineers actually crunch the numbers in the real world? We use a standard formula for hysteresis loss, which is denoted as P subscript H. Now, I know it might look a little dense at first glance, but let's break it down piece by piece so you can see exactly what's driving the heat up in your machines. All right, so pH is our total power loss in watts. Next up is that Greek letter eta, which stands for Steinmetz's constant. This one is absolutely crucial because its value depends entirely on the specific magnetic material you're using. Then, we multiply that by Bmax, which is the maximum flux density, times F, our frequency in cycles per second, and finally V, the total volume of the magnetic material. You'll notice right away that the inherent type of material you choose, that eta value, and the sheer volume of the core both play massive roles in how much energy is ultimately going to be wasted. We know the cause, we have the math. Let's look at Section 5, the engineering solution. When we compare materials, the difference is striking. On one hand, if you have a material with a wide hysteresis loop, you're looking at a huge area, high internal friction, and a ton of wasted heat. On the flip side, a narrow hysteresis loop means a smaller area, very low internal friction, and a highly efficient material. Remember, it all comes back to the area of that loop dictating the energy loss. I think the core takeaway here is summed up perfectly by this quote from our source text. A suitable magnetic material having a minimum hysteresis loss, which has the narrow hysteresis loop, is used for making these electrical machinery parts. The definitive fix to this heating problem isn't some complex mechanical workaround. It's actually just smart material selection. By intentionally choosing magnetic materials that naturally form narrow loops, engineers can drastically cut down on that internal molecular friction right from the start. Which leaves us with a really fascinating question to ponder. If every single magnetic reversal inherently wastes some energy as heat, How might this physical limitation completely change how we design the ultra-high-frequency machines of the future? It is such a cool challenge for the next generation of engineers. Anyway, thank you so much for joining me today. I really hope this explainer brought you some solid clarity on what is a somewhat hidden but incredibly important topic. Please make sure to subscribe to the Kognito Key channel and go ahead and like and share this explainer with your peers. Keep exploring, keep learning, and I will catch you in the next one.